Chapter 4, Gyro Filter Tuning. In this chapter, we're going to be looking to optimize the amount of filtering applied to the data collected by the gyro on your drone. And this gyro data is really important because it's used to control the angle of the drone in the sky, and that's the foundation for all of the tuning that we're going to be doing later on in this course. In order to get the optimum amount of filtering, we're going to be looking at the gyro low pass filters to remove high frequency noise, and then we're going to be using harmonic notch filters to remove specific sources of noise like motor frequencies and frame resonances. And we're going to be driving those harmonic notch filters with a variety of different methods: RPM data and fast Fourier transform data from the FFT engine inside ArduPilot. We're also going to be looking at throttle controlled notches and static notches as well, trying to cover all the information that you will need in order to get the ideal amount of gyro filter tuning, which is just enough to remove all the problematic sources of noise, but the minimum level of filtering required to do that, so that we minimize the amount of delay in the filtering and so the drone can respond nice and quickly. It's a lot to cover, and this is a longer chapter, so I wish you the best of luck. Let's dive right into it. So why do we need gyro low pass filters anyway? Well, fundamentally it comes down to the fact that the gyro in a drone is sensitive both to rigid body rotations of the drone, so where the drone is moving all as one piece, and it's also sensitive to vibrations of the drone, where the overall body of the drone is still, but some part of the drone is moving relative to some other part, for example, a propeller blade. Vibration can be generated by spinning motors and props, and they typically generate a lot of vibration, but it can also be generated by resonance of the drone's airframe and payload. And the best way to visualize that is to just use an animation. So here's a couple of resonant modes of vibration of this drone that you're looking at now. You can see that the frame can bend and twist and move, and even while the drone overall is still, different parts of the drone can be moving relative to other parts, and the gyro can pick that up really, really well. One of the challenges we face is that the energy in vibrations, in noise, is usually much, much higher than the energy in rigid body rotations of the drone. And that's because the vibrations are at higher frequencies, and when something is moving at a higher frequency, it is rotating or twisting or bending much, much faster, and so the gyro picks that up as a much larger signal. Fortunately, the real movements of the drone are at low frequencies, below about 30 Hertz, because a drone like this can't really rotate as a rigid body any faster than about 30 Hertz. It's just not physically possible because of the moment of inertia that the whole drone has as a rigid body. But vibrations occur at much higher frequencies, so they're typically above 50 Hertz, but it does depend on prop size and RPM. So we can use a low pass filter, the gyro low pass filter, to take advantage of this and attenuate the high frequency vibrations without affecting the real rigid body rotations of the drone. Unfortunately, the gyro low pass filter does have some trade-offs that we need to be aware of. Here's a plot of the attenuation of a gyro low pass filter with frequency. You can see that as the frequency increases, the amount of attenuation that the gyro low pass filter is providing is increasing with a larger negative decibel number. So at a higher frequency, there is more attenuation. But it also adds delay, and it adds delay to all frequencies. So the lower the cutoff frequency of the gyro low pass filter, the more delay is added. So you have this trade-off. If you want more low pass filtering, more aggressive low pass filtering, you have to tolerate more delay in your filter loop. And that's not due to the CPU, it's not due to the calculations, it's just a mathematical product of the filter. The more filtering you want to do, the more delay there's going to be. This delay slows the reaction of the drone to the data coming in from the gyro. So it slows its reaction to air turbulence, it slows its reaction to control inputs, and can, in the worst case, make the drone unstable, because if there's too much delay, it just can't keep control of itself. So the goal with all of this filtering is to achieve enough attenuation to squash the noise, but keep the delay as low as possible to improve the reaction to control inputs and turbulence. Because our goal is to minimize the delay of the gyro low pass filter, we want to gradually increase the cutoff frequency of that gyro low pass filter as high as possible without letting noise through. But we can't do this just yet because our main adversary is this noise peak here, which is the fundamental motor frequency, or it could also be the first frame resonance depending on the build. We need this peak to be below about minus 50 dB in the post-filter data to make sure that that noise isn't going to affect the flight performance of the drone. And we could, of course, do that with the gyro low-pass filter, but it's much more efficient and effective, and we can do a much better job with less delay if we use the harmonic notch filters to deal with peaks like this. The gyro low-pass filter is much better suited for dealing with this high-frequency noise up here, rather than these peaks. So what are harmonic notch filters? Harmonic notch filters are another type of software-defined filter in ArduPilot, and rather than providing like a broad attenuation that increases with increasing frequency, notch filters provide a very high degree of attenuation around a specific target frequency. So you can see here that I've added a notch filter on top of the gyro low pass filter I showed you before, and you can see that it has a lot of attenuation at a particular target frequency. They create much less delay for the amount of attenuation they give compared to a low pass filter that would achieve the same effect at that particular frequency. They're much more efficient in terms of delay. The narrower the notch that you can make, so that the tighter it is, the narrower it is, the less delay it causes, and that's better. But of course, if you have a very narrow notch, you need to target it very, very precisely so that you're attenuating just exactly where you need the noise to be removed. Because obviously if the notch is very narrow, if it's slightly off target, it's not going to do anything at all. Tuning notch filters is about targeting narrow notches, as narrow as possible, exactly on top of where you have noise from motors or from the frame resonance, and eliminating that noise whilst adding the minimum possible amount of delay. Once you have your logging settings set up correctly, it's time to enable the harmonic notch filter bank. Now to do that, you can go into the config tab in Mission Planner and the full parameter list and search for ins_h notch in the bar on the right hand side. So ins_h notch. Then you're going to want to set ins_h notch enable equal to 1. That's going to enable the harmonic notch filter bank, and you're going to need to write that parameter and then refresh the parameter list in order to see all of these additional harmonic notch parameters. Then you're going to want to set the ins_h notch harmonics equal to 7. Now that's a bit mask that will enable 3 harmonic notches, one at the fundamental frequency, one at the first harmonic, so twice the fundamental frequency, and one at the second harmonic, which is 3 times the fundamental frequency. That is a typical good setup for bi-blade or tri-blade props, and I will talk to you later about how we can tune that so that you get the right number of notches. But this is a good starting point. You're going to want to set ins_h notch mode equal to 3. That's taking the notch information, so where to target the notch, from the ESC telemetry. So it's looking at the motor RPM to target the notch. That's going to be the best. If you know that you don't have RPM telemetry for whatever reason, then I'll talk about how you can set up FFT tracking later on. You're also going to want to set ins_h notch options equal to 0. And that's just to begin with. We don't need any of the fancy options right now. I'm going to be showing you how to set up bidirectional D-Shot to get RPM data directly from the ESC over the D-Shot protocol. So to do that, you're going to want to go again into the full parameter list, so the config tab, full parameter list in Mission Planner, and search for RPM. That will bring up all of the relevant settings. You're going to want to set RPM1_type equals 5, and that will set bidirectional D-Shot as the source for the RPM1 sensor. You're also going to want to set RPM1 ESC mask equals 15. That's, again, it's a bit mask, and that will set it true for the first 4 motors. If you have more than 4 motors, then you're going to need to go into that bit mask and tick on every motor that you have bidirectional D-Shot data for. You're also going to want to set servo BLH BD mask equals 15 so that you are enabling bidirectional D-shot on all 4 motors. Again, if you have more than 4 motors, go into this bit mask and enable all of the channels that you have motors on. Then you're going to want to set the servo BLH poles. Now, this is the number of magnets in the motor. When the ESC reports RPM, it reports electrical RPM. And electrical RPM is not the same as the mechanical RPM of the motor. The conversion between electrical and mechanical RPM is taken care of by RGPilot, but to do that, it needs to know how many magnets there are in the rotor of the motor. So 14 magnets is typical for a 4-inch to about a 10-inch prop size, motors for that kind of size of drone. If you're flying a smaller drone with maybe 3-inch props, you're likely to only have 12 magnets in the motor. If you have a bigger motor for a larger prop, you're likely to have more magnets than 14 and sometimes a lot more. If in doubt, just count them. Just count how many magnets there are in the rotor of the motor, and that's the number you need to set in servo BLH poles. After you've done that, go to servo D-shot ESC, and here you're going to need to set up the protocol over which you're communicating with the ESC to get the RPM data. So if you have a KISS AM32 or BLHeli32 ESC, you can set that to 1. If you're using a BlueJay ESC, then you can set that to 2. And that information is going to be available from the manufacturer of your ESC, what firmware that ESC is running. All the latest ESC firmwares, so the latest versions of BLHeli32, the latest versions of AM32, KISS and BlueJay, all support something called extended D-shot telemetry, where you can get more than just the RPM data back from the motor. So you can also get things like voltage, current if the ESC supports it, temperature. This can be very useful just to get more data, more telemetry back from the ESC to see how it's performing. And it's all done over that extended D-shot protocol, so you don't need any additional wires or anything like that. If you want to try this, then you can use settings 3 and 4, which is basically the same as 1 and 2, but adds this extended D-shot telemetry function. Once you've downloaded the log and you hit review in Mission Planner, then you should get a plot that looks something like this. The first thing to do is to check the RPM data in your log to make sure that bidirectional D-shot is working correctly and you're getting accurate RPM information. You can find that under the ESC group, and then you'll have 0, 1, 2, 3 for the 4 ESCs, and within each of those, the RPM data is available. If you tick it on, it should plot the RPM data for all of the motors. And ideally, you're looking for a nice smooth line that reflects what you did during the flight. As you can see in this log, I'm getting these sharp spikes on ESC0 for the RPM data, and it continues throughout the flight. This is very typical of a DMA conflict on a particular pin. So here the servo output 1 pin clearly has some sort of conflict with something else is also using that DMA channel. If that's the case, the best thing to do is to rewire the flight controller and ESC so that you're using a different servo output for the channel that's got a DMA conflict. So in this case, I actually rewired servo output 1 to servo output 5 so that I could just use servo output 5 instead of servo output 1. That fixed the issue for me completely. You can also do some other things like change the servo BLH BD mask so that you ignore that channel and you don't get any bidirectional D-shot data from there, but that's not ideal because obviously we'd like to know what the motor RPM is. And in the worst case, you can use the dynamic FFT rather than bidirectional D-shot to drive your harmonic notches. And we'll talk about that in a future video, but that's definitely going to work less well than using the RPM data. So don't advise that either. I would just consider rewiring it. So try and use another servo output instead of the pin that's got the conflict. Even if your ESC doesn't support bidirectional D-shot or RPM telemetry, you can still use RPM data to drive harmonic notches if you have a separate RPM sensor. If you want to use a separate RPM sensor, you can set it up by going into Mission Planner, Config tab, Full Parameter List, and searching for RPM1. That's going to bring up all the information for the first RPM sensor, and you're going to set the RPM1 type according to your hardware. So
In this guide, we're going to assume a simple GPIO sensor, which is the most common, but you may have a different type, like drone CAN or something else. Once you've set the type correctly, you're, for a GPIO sensor, going to want to set RPM1 max to the maximum realistic sensor value that you might see, which is going to be the kV of your motor multiplied by the maximum battery voltage when it's fully charged, multiplied by the number of triggers per revolution. So if you have an RPM sensor that triggers multiple times for one revolution of the motor, then you're going to want to multiply up that value. You want to set the RPM1 min to the minimum realistic sensor value, which is going to be the RPM that the sensor reports, and reduce that a bit from the idle RPM when the motor is just spinning without doing anything. So if you just arm the drone but don't try and take off, that will give you the kind of idle RPM of the motor. You can look that up in a log, just reduce it by, let's say, 20-25%, and that's a good sensible minimum value. You want to set the RPM1 pin to the GPIO pin that you're using for the sensor, and you want to set the RPM1 scaling to 1 divided by the number of triggers per revolution. So if you have an RPM sensor that triggers 4 times for each revolution, because you've got a Hall sensor and you've got 4 magnets, then the scaling factor is going to be 0.25. If you've got 1 optical tape, then your scaling factor is going to be 1. This setup is going to be exactly the same for the RPM2 sensor. If you decide to use 2 RPM sensors to get more information about the RPM of your motors, put one of the sensors on a clockwise motor and one of the sensors on an anti-clockwise motor so that you see a difference in RPM when you're doing your moves, and also try and place the sensors on opposite sides of the quad so that you get some response to, let's say, a roll move as well, because that will be helpful just to make sure that your notches are tracking all the RPM values, all the frequencies that are going to be useful, that motors are going to be spinning at, so that you get the best noise attenuation. Once you've set up the RPM sensors, go into your harmonic notch setup and set ins H notch enable equals 1 to show the notch parameters for the first bank of harmonic notches. Again, this is in the full parameter list in the config tab. Set your ins H notch harmonics to 7 for 3 harmonics for tri-blade props, or of course you could set it to 3 if you only want 2 harmonics because you're only using bi-blade props. Set ins H notch mode equal to 2 to use the RPM sensor data to drive the harmonic notch, and set the ins H notch FM rate to 1 for no scaling, and ins H notch ref to 1 as well. For ins H notch options, you can set that to 0 to begin with. That should enable all of the harmonic notch functionality using that RPM sensor data. And then you're going to want to follow along with the RPM notch tuning that I cover later in this guide. Even though you're using an RPM sensor and not bidirectional D-shot, all of that information is still relevant for tuning the harmonic notch frequency and for what some of the options might be useful for. Once you've set up the RPM sensor correctly, you need to check that the data is being reported accurately. And for that, you're going to go into Mission Planner, the Data tab, and review a log. And within the log browser, you're going to go to the RPM section. And you can see that we have 0 here. And if you have a second RPM sensor, you'll also have field number 1. Within the 0, you'll see RPM. Just tick that on and double check that there are no spikes or dropouts of the RPM data during the log, and that the RPM sensor is reporting the true RPM value of the motor. And this will confirm that all of your scaling settings are correct, and that the number of triggers that the RPM sensor has per revolution is being correctly scaled so that RGPilot knows what the true motor RPM is. And that's really important. If you have some multiple of the true motor RPM, then all of your notch filters are going to end up in the wrong place. Once you've done the hover test, you can download the log using Mission Planner, the same as we have before. But this time you're going to be reviewing the log using the RGPilot Web Tools filter review page, which is available at this URL, and there's also a link for it down in the video description. Click through to this page, you should see something like this, and there's a button saying Choose File. Choose the log file that you just downloaded from the drone over USB,
And then once it's uploaded and opened in the review tool, you should see that the flight data chart is populated with what you did during the flight. Just check that that data looks correct and that there are no gaps or logging dropouts. Once everything has loaded up correctly, if you scroll down to the IMU spectrum section, you should be able to tick on the pre-filter XYZ, post-filter XYZ, and the notch tracking notch 1 tick boxes. And then you should see a chart that looks something like this, with 6 lines on it and 3 vertical grey lines with grey bars around them. If you're seeing all of this, that means that your logging settings are working correctly and that you have all the information you need to be able to tune your gyro filters to perfection. You'll also see the effect of the gyro low pass filter very clearly in this plot, because you can see that in the post filter data, which are these lines down here, that the amount of noise, the amplitude of the vibrations at high frequencies are much lower compared to the pre-filter. That's the effect of the low pass filter, which we'll talk about now. In order to validate our notch tracking and tune our harmonic notches, we need to use the IMU spectrogram section in the ArduPilot Filter Review web tool. If you scroll down to this section, you should see a plot that looks something like this. Turn off the notch tracking for now if it's enabled, because we want to zoom in so that I can show you the key features of this plot. Once you've zoomed in on a few seconds of hovering, we can look at the key features that we're going to be using in this IMU spectrogram. The first thing to look for is the red noise power at very low frequencies, so below 30 Hz. This is the rigid body movement of the drone. This is the signal that we're looking to capture from the gyro that tells us how the drone is moving. Then if we move up from there, you should see a red horizontal line at the hover frequency of the motors. So this is the RPM of the motors in a hover divided by 60. That will give you approximately the frequency that you should be looking for this horizontal line. If you don't know your RPM at hover, you can approximately calculate it by taking your battery voltage, multiplying it by your motor kV, and then multiplying by your hover throttle. That will give you an idea of the RPM that you're looking for. Divide that by 60 to get the frequency, and you should see a horizontal line. You should also be able to see a horizontal line at twice the hovering frequency. Now, this is likely to be strong if you're using 2-bladed props, but it may be very weak and in fact almost invisible if you're using 3-bladed props. So see if you can see that. I have a little bit of one here, but it's quite faint. Then we're going to be looking for a red line at 3 times the motor frequency. And this is likely to be very strong if you're using 3-bladed props, but might be weak or nearly invisible if you're using 2-bladed props. And it's easy to understand why this might be. If you've got a 3-bladed prop, you have 3 blades passing over the arm, let's say, every rotation. So you're going to create a lot of vibration at 3 times the motor frequency. If you only have 2 blades on the prop, then the blades are passing over the arm twice per rotation, and so you get a lot of noise at twice the motor RPM. Now let's go ahead and turn on notch tracking. Now, if you have RPM notches set up correctly and you've done everything correct in the setup in the early part of this video, you should see these horizontal lines sitting right on top of the red line for the motor RPM. So you can see that we've got a notch tracking directly on top of the fundamental RPM frequency. And we also have a second notch tracking directly on top of twice that frequency, and a notch tracking directly on top of 3 times that frequency as well. So this shows that the RPM notches are working correctly and they are very accurately targeting the motor frequencies. You might have a question at this point of, well, we've got 3 notches, but I can see a horizontal red line at 4 times the motor frequency. Do we need a 4th harmonic there? And to answer that, we need to look a little bit deeper. Up until now, we've been looking at the pre-filter data. So that's the data from the gyro before any of the software filters are applied. So before the gyro low pass filter and before any of the harmonic notches. If on the IMU spectrogram we tick post filter instead, then you can see the effect of the gyro low pass filter and the harmonic notches. And in my case, that makes this fourth harmonic completely disappear, because that fourth harmonic is at such a high frequency, nearly 500 hertz, that the gyro low pass filter does a fantastic job of just crushing all that noise away, and so we don't need a notch there. If you still see in the post filter data that you have a strong horizontal line of noise at 4 times the motor frequency, then you should go into INS H-notch harmonics and turn on a 4th notch to target that frequency. But if you don't see it in the post filter data, then you don't need to add that extra notch, and we don't want to add more notches than we need, because every additional notch adds delay, and if it's not providing any benefit, that delay is just hurting our flight performance. Now that we're looking at the post-filter data, go ahead and turn off notch tracking so that you can clearly see how much noise is getting through your filter bank and being passed onto the PID loop. In my case, you can see that some noise is still getting through at 3 times the motor frequency, and quite a significant amount of noise is getting through at the fundamental motor frequency, despite the fact that we have RPM notches tracking these frequencies. This is not uncommon, and there are settings in ArduPilot that we can use to improve on this. At the moment, with the settings that we have, the notches are tracking the average of all 4 motor RPMs. So we're measuring all 4 motor RPMs separately, averaging that number, and that number is being used to drive the location of the harmonic notch. So this works great if all of your 4 motors are at exactly the same RPM, because then they all have exactly the same frequency and the notch is targeted right on top of all of them. The problem occurs when the motors are spinning at different RPMs, which will often happen if you've not got a perfectly centered center of gravity, or you're giving some yaw input, then you'll have some differential motor RPM. At that point, the notch isn't directly on top of all 4 motors. Some of the motor noise is going to be moving either side of the notch, and that means it's going to start getting through, because we know that those notches are very narrow and very targeted, and if the noise is just slightly to either side of the notch doesn't have any effect. The performance of RPM-driven harmonic notches in ArduPilot can be greatly improved through the use of the multi-source option. What this effectively does is, rather than taking the average of all 4 motor RPMs and putting a notch there, it creates 4 notches, 1 for each motor RPM, and all of those notches track the motor RPMs exactly. This means that even if you have 2 motors running at a higher RPM, 2 at a lower RPM, the notches are tracking individual motors, and so you get perfect attenuation of the motor noise. To do this, you're going to want to change some settings. So if you change INS H-notch bandwidth to INS H-notch frequency divided by 4. The reason we're making the notches narrower before enabling multi-source is that when we're adding 4 times as many notches, we have to make the notches narrower so that the delay doesn't get out of control and cause control issues. You can either do this directly in Mission Planner in the Config tab full parameter list, or you can actually change them in the Filter Review web tool, and then you can see the effect that those filter settings would have had on the log. It doesn't change the settings on the drone, it just kind of gives you a sneak peek of what it might look like if you change those settings. So go ahead and change the bandwidth to 1/4 of the H-notch frequency, and then set H-notch options equals 6 to enable multi-source, and also to set the notches to update at the loop rate. When you have very narrow notches that are tracking individual motors, you really do need them to move nice and quickly to follow those motors closely, and so we want to update them at the loop rate rather than at the standard rate, which I think is only 200 hertz. Once you've done that, you can hit Recalculate Filters in the Filter Review web tool to see the effect, or you can just apply these settings on your drone and go and take another test flight. Hopefully you can see exactly the effect that I described, which is that rather than just having a single notch at the fundamental motor frequency, a single notch at twice that frequency, and a single notch at 3 times, we now have 4 notches for each of the motor harmonics, and those 4 notches are driven off the individual motor RPMs for the 4 motors on the quad. If you have 6 or 8 motors, you are going to have 6 or 8 notches. And if that's the case, you're going to need to further reduce the notch bandwidth in order to keep the delay of those notches nice and low so that it doesn't affect the control of the quad. If you can see that all 4 notches are tracking the motor RPMs really nicely, then everything is working and you can move on. Once you've got multi-source working correctly and the notches are tracking accurately, we need to tune them for best performance and minimum delay. To do this, we need to set IN's H-notch frequency to be the frequency at which motor noise just starts to become a problem. So we can see this in the IMU spectrogram if we just do a log where we throttle up very slowly from 0 throttle up into a hover, and you can just look at the log and see, well, at what point does the motor noise start to become a problem? For me, it's just right around 80 Hertz. So that's the right value for IN's H-notch frequency. If you have a drone with much smaller props than 8 inches, you'll probably find that your motor noise doesn't become a problem until a much higher frequency. But once you've found that frequency, that's what you need to set IN's H-notch frequency to, and you can find that in the full parameter list in the config tab of Mission Planner. You also want to reduce the IN's H-notch bandwidth as far as possible. The narrower you can make those notches, the less delay they will cause, and provided that the notches are still wide enough to attenuate all of the motor noise, then there's no benefit to them being wider than needed. So we want to kind of reduce them, squeeze them as tight as we possibly can. You can do that by reducing the IN's H-notch bandwidth parameter, which you'll find in the full parameter list in Mission Planner. Just step that down gradually as far as you possibly can. And you want to go until you start seeing some motor noise bleeding through on either side of the really narrow notches. And then you can see that in the post-filter data in the IMU spectrogram in the filter review tool. If you start seeing motor noise bleeding through, then step back a little bit. So increase the bandwidth slightly, maybe 10% or so, just so that you've got the minimum bandwidth that still captures all of the motor noise and attenuates it effectively. Let's start by asking the question, what is the dynamic FFT? FFT stands for Fast Fourier Transform, and it's a mathematical tool that allows you to take a chunk of time series data from the gyro, usually about half a second or so, and convert it into the frequency domain. So we can see the component frequencies in that signal, in that time series signal, and how much energy, how much amplitude there is of each of those frequencies, and kind of plot that on a frequency plot. If we see particular peaks in that plot with a high amplitude, a high amount of energy, the frequency of those peaks can then be passed to the harmonic notch filters to drive the location of a notch filter to attenuate that peak specifically. When talking about noise from motors and props, if you have the choice between using the dynamic FFT or RPM data to drive the harmonic notches, RPM data is always going to be better. With motor RPM data, you know the exact frequency of the motor noise immediately with no delay, and you can update it very, very rapidly. With the dynamic FFT, you have to calculate the frequency of the motor noise, and you have to calculate it with a nasty trade-off. The better the frequency resolution you want, so the more precise you can be with placing the notch, the more gyro data you have to sample. So if you want a frequency resolution of 2 Hertz, you need to sample for half a second of time. And that's a long time in the world of notch filters. And that means that your notch filter is always going to be half a second delayed behind where it would ideally be. So if the motor RPMs change, that notch filter is always going to lag behind. And that means you can never make the notch filter as tight as you can if you had up-to-date RPM data. Dynamic FFT is extremely useful in addition to RPM filtering in certain cases. So if you've got RPM filtering and that's working well, but you've still got something like a frame resonance that is coming through and it's not related to the RPM, then the dynamic FFT is the perfect tool to lock onto and track that frame resonance. It can also be used for motor noise if you don't have any RPM data, but RPM data should always be available. It's 2025. We should have that data from the ESC or from an RPM sensor. It's much more difficult to get dynamic FFT working and tuned compared to RPM filters. There's more parameters to work with, but we're going to go through that now, and I'm going to give you all the information you need to get the FFT working really well for both frame resonances and, in the worst case, motor noise. Now let's look at the rare case where you want to use the dynamic FFT to address motor noise. Now, you're only going to want to do this if you don't have any RPM data and you have no other way of targeting those notches accurately. But I'm going to include a description here just for completeness. You want to set FFT enable equals 1 to enable the FFT engine as before, and set FFT max hertz slightly above the fundamental motor frequency at full throttle. So the motor RPM divided by 60 at full throttle. And if you don't know that, you can estimate it by taking 0.8 times your battery voltage times the kV of your motor and dividing by 60 to give you an idea of the maximum motor RPM frequency. You want to set FFT min hertz to the lowest frequency where motor noise is seen in your log. So you can obviously find that by very gradually throttling up from zero throttle and just seeing when motor noise starts to appear, what frequency it starts to appear at. You want to set FFT num frames equal to 0 because FFT needs to be reactive to changing motor RPM. It's not going to be possible if you average multiple frames. You want to set FFT options equals 1 to apply the low pass filters before doing the FFT. That will help the FFT lock in on the lowest motor peak. And then of course we can use the harmonics option to apply filters at multiples of that frequency as well. Set the FFT window equal to 1024 if CPU allows, or as high as possible. Once you've enabled and set up the FFT engine, it's time to look at the harmonic notches. And for motor noise, we're going to use the first bank of harmonic notches. So ins H notch enable equals 1 to enable the first bank of harmonic notches. You can set ins H notch mode equals 4. That will use the output from the FFT engine to drive the location of the notch. Ins H notch frequency equals FFT min hertz because we don't want the notch ever going below the minimum frequency that the FFT engine is looking for, because that's going to be the frequency where motor noise starts to appear. There's never going to be anything below that. You want to set ins H notch bandwidth equal to ins H notch frequency over 2. That's a good starting point for the width of the notch, but obviously we're going to try and make it narrower in tuning if we can. Set ins H notch ref equals 1 because we don't need any scaling when we're taking data from the FFT engine. And set ins H notch FM rate equals 1 to prevent the notch ever going below ins H notch frequency, because obviously that's going to be the minimum frequency where we see motor noise. Set ins H notch harmonics equal to 7 for tri-blade props, that's 3 harmonics. If you've got bi-blade props, you may only need 2 harmonics or you may need 4 harmonics. You're going to have to check in logs to see what applies, and it's the same as for the RPM notches that we talked about earlier. To start with, we're going to talk about using the dynamic FFT filtering to address frame resonances that are not being well handled by your RPM filters. In this case, we're going to be using the FFT to drive the second bank of harmonic notch filters because the first bank of harmonic notches will be driven by our RPM data. You're going to go into the config tab in Mission Planner to the full parameter list and search for FFT in the box on the right hand side. Then set FFT underscore enable equals 1 to turn on the FFT engine. And then you're going to want to set FFT max hertz to the upper limit where you see problematic frame resonances. So you want to set that a bit above the frame resonance that you're trying to target. FFT min hertz should be set a bit below the frequency that the frame resonance occurs at. So you're sort of bracketing the problematic set of frequencies with min hertz and max hertz. The FFT number of frames is how many FFT frames to average together to get a more accurate frequency for the noise peak. Now, in this case, I would normally set this to 0 or maybe 1 if you're able to be using a large FFT window. And for reasons that I've explained before, we do want to use as large an FFT window as possible. So ideally the maximum of 1024 if CPU load allows, or at the very least as high as possible. For the FFT options, you want to set that equal to 1. That's a bit mask. That will apply the gyro low pass and the RPM filters before doing the FFT calculation. And that means that the FFT won't see the motor noise, and the gyro low pass filter will also attenuate high frequency noise. That will help the FFT to lock on to the low frequency noise peak of frame resonance that you're looking to target. So yeah, FFT window as large as possible. And I'll talk later about how you check CPU load to see if this is okay. And then you're going to want to set ins H notch
2_mode equals 4. Now that will set the second bank of harmonic filters to use the FFT to drive those second bank of harmonic notch filters. Now that we've enabled and set up the FFT engine, it's time to enable the second bank of harmonic notch filters to target the frame resonance. And to be clear, you only want to do this if you have seen a frame resonance in the log that you need to target. That will be a strong peak of noise that is not a multiple of the motor RPM frequency. If you've got one of those, then you can use the second bank of harmonic notches to target it. If you don't have one, then don't enable the notches, because adding more notches only increases filter delay and that will hurt flight performance. If you do have a frame resonance to target, you're going to want to set ins h notch to enable equals 1. That will enable the second bank of notches and reveal all the additional options. You want to set the ins h notch to mode to 4 to use the dynamic FFT result to drive the location of the harmonic notch. You want to set ins h notch to frequency equal to FFT min hertz, because you don't want the notch filter ever going below the frequency that the minimum frequency that the FFT is looking at. You also want to set ins h notch to bandwidth equal to ins h notch to frequency divided by 2. That's a pretty suitable width for the notch to begin with, but of course we are going to tune it and try and narrow it if we possibly can later on. Set ins h notch to ref equals 1, because no scaling is required for using the dynamic FFT output. And ins h notch to FM rate equal to 1 also, to prevent the notch ever going below ins h notch to frequency. We don't want it ever to drop below FFT min hertz, because we're never going to have a target that low. Set ins h notch to harmonics equal to 1, because we only want a single notch in this case. There aren't usually multiples of the frame resonance with lots of noise, not in the same way that is typical for motor noise. Usually you just have a single frame resonance at one frequency and you don't see anything at multiples of that frequency. So a single notch is appropriate here. So ins h notch harmonics equals 1 to apply just one notch. Applying additional notches when there's not noise there to filter obviously adds delay and hurts flight performance. Set the ins h notch options equals 0 for a single frame resonance. So we don't need any of the other options on if you just have one frame resonance. If you've got several different frame resonances and you're trying to target them with multiple notches, you could use ins h notch to options equals 2 to turn on multi-source. What that will do is that will take the first 3 peaks from the FFT, the 3 largest peaks that the FFT sees, and put a notch on each of them. So if you have up to 3 frame resonances, then multi-source can be a good solution for that. If you only have one frame resonance, you don't want to use multi-source, because again, it just adds more delay, more notches, more delay. We should take a moment to talk about static and throttle-based notch filtering. These are older approaches that drive a bank of harmonic notch filters using either a fixed frequency or a frequency that scales with throttle position. I don't advise using either of these methods nowadays, because they're both very brittle filtering approaches and they can be rendered completely ineffective by changes such as changing your props, changing your motors, changing the operating altitude of the drone. All of these can affect the relationship between motor RPM and throttle position. And if you've got different manufacturing tolerances on frames or you're running different payloads, that can affect the exact frequency of a frame resonance, which renders a static notch less effective at dealing with that noise. I would advise using RPM data to drive your first bank of harmonic notches, and if you have frame resonances that are visible, FFT engine data to drive a second bank of harmonic notches. This is a durable approach. The RPM data will adjust to changing props, changing motors, changing altitude, and the FFT engine will be reactive to changes in the resonant frequency of any frame resonances due to changing manufacturing tolerances or changing payload. If, however, you're using FFT for your motor noise because you have no RPM data available, in that case, you may need to use a static notch to deal with frame resonances, because it's not usually possible to use FFT to deal with both motor noise and frame resonances, even with multi-source. So that is a trade-off that you may have to make, and that's why it's a really good idea when you're designing a drone to make sure that you're going to have RPM data available. If you don't have RPM data available on your drone and you're using the dynamic FFT to drive a first bank of harmonic notches to handle motor noise, if after that process you still have a problematic airframe or payload resonance that you need to deal with, then a static notch may be the right approach for you. If you want to set up a static notch, you can set ins h notch to enable equals 1 to enable the second bank of notches. You'll find all these parameters in the Mission Planner config tab full parameter list. And then you're going to set ins h notch to mode equal to 0 to use a static notch. Ins h notch to frequency is going to be your target notch frequency, the frequency you want the notch centered around. And you're going to set ins h notch to bandwidth equal to ins h notch to frequency divided by 2 as a starting point. You'll determine the frequency that you need the notch at from logs, from just looking at the FFT spectrum from some of your logs. And you're also going to want to set ins h notch to ref equal to 0 to disable updates of this notch. You can set this up and it's just going to put a notch in one place and it's not going to move. So make sure to check in the logs that the noise that you're trying to deal with doesn't change frequency with throttle position or with the weight of the drone if the drone's weight is going to change. You want this, you want to use this notch to deal with noise that is always at exactly the same frequency, and you can put a notch on there. You may find that you need to slightly move this notch between different drones, even of the same design, because certain types of resonances can be very sensitive to just the manufacturing tolerances of the drone or the weight of the payload or the exact configuration of the setup. So when you're using a static notch like this, just be aware that it is quite a brittle filtering approach and you will need to double check probably every drone to make sure that it's in the right place. If you don't have RPM data available on your drone and you don't want to use the dynamic FFT to drive your first bank of harmonic notches, but you still want to use harmonic notches to filter motor noise, then you may want to consider throttle-based notch filtering. If you're going to use throttle-based notch filtering, you're going to want to go into Mission Planner, Config tab, full parameter list, search for H notch just as before to bring up the harmonic notch filter parameters. Set ins h notch enable equal to 1 to enable the first bank of harmonic notches, and then ins h notch mode equal to 1 to use throttle-based notch scaling. This needs a number of parameters which you're going to need to determine from logs. The first is the ins h notch frequency, which is the frequency of the motors, the RPM of the motors when the drone is hovering. So you're going to look at the frequency of noise that is produced in a hover. You can determine that from logs. You can measure it using a temporary RPM sensor, and then of course remember to divide by 60 to go from RPM to frequency in hertz. And you can also, if you're using the FFT, use FFT frequency hover, which is a parameter which is looking to learn the hover noise frequency. Now, this is not always accurate, and so don't just use this value. Make sure you check it against the log and check that it's correct and that it's picking up the fundamental motor frequency and not the second or third harmonic. Sometimes the FFT will lock on to the second or third harmonic rather than the fundamental. Obviously, for the throttle-based notch filtering, you want the fundamental frequency in a hover. Set ins h notch bandwidth equal to ins h notch frequency divided by 2 as a good starting point. Obviously, we're then going to tune it the same as we do for all notch filters. And you want to set ins h notch ref to the hover throttle position. Now, you can determine this from log data, and you can also find this under the mote thrust hover parameter. But again, like with the FFT frequency hover, this is not always accurate or correct. So you want to check that parameter and then double check it against a log to make sure that that is truly the hover throttle that you were at during the hover and that it's not picked up some other value. Sometimes, particularly if you have a very high thrust to weight ratio drone, your hover throttle might be below 12.5%. If it's below 12.5%, then often the motor thrust hover parameter won't pick it up correctly. So make sure you double check it against a log just to make doubly sure. Once you've set those parameters, you're going to want to look at the ins h notch FM rate to determine how far below your hover throttle position the harmonic notch filter is going to scale. And the only way to determine this is to look at logs. You're going to want to look at a log and determine the minimum throttle setting that causes problematic motor noise, which I'm calling TN min here, throttle noise min. So here on this example log, again, this is a very high thrust to weight ratio drone, but we get some significant motor noise appearing at 80 Hertz at just around 1% throttle, and my hover throttle is around 8%. So here we're going to divide the throttle position that motor noise appears at, Tn min, by the hover throttle, which is about 8%, to get a ratio of 0.125. It's likely that your ratio is going to be a lot larger than this, particularly if you're using a larger, heavier drone that hovers at a higher throttle position. You're going to want to set the INS H-notch harmonics equal to 3 for two-bladed props typically, and INS H-notch harmonics to 7 for three-bladed props. That's going to provide the right number of harmonics, scaling from the fundamental frequency to cover the main noise that's going to be produced by two and three-bladed props respectively. However you're targeting your harmonic notches, it's always beneficial to tune the bandwidth of your harmonic notches once you've got them correctly applied. If you can reduce the bandwidth of a notch, you can reduce the amount of delay it causes, and that will help improve flight performance. Obviously, if you reduce the bandwidth of a notch too much and you make it too narrow, you'll start to see noise bleeding through either side of the notch, and the notch will be ineffective. So there is a tuning process that you need to go through to find the minimum suitable notch bandwidth. To do this, we're going to go into the Mission Planner config tab, full parameter list, search for INS H-notch bandwidth or INS H-notch 2 bandwidth, depending on which bank of harmonic notches you're looking to tune. And you're going to start to gradually reduce in steps of 10 or 20% the INS H-notch bandwidth number. As you bring that bandwidth down, the delay of the notch is going to go down and the notch is going to get narrower and narrower. Continue until you start seeing the noise, so either the motor noise or the frame resonance, bleeding through in the post-filter data. So you can see the notches being correctly applied, but you can also see that there is orange or red noise coming through despite the fact the notch is there. And that's going to be caused simply because the notch is now so narrow that most of the noise is going either side of it. Depending on how you're targeting the notch, whether you're using FFT-based, throttle-based, a static notch, or RPM-based notches, either through bidirectional D-shot, ESC telemetry, or an RPM sensor, that's going to depend on how narrow you can make the notch. RPM data, whether from bidirectional D-shot or an RPM sensor, is usually more accurate than FFT or throttle-based or static notches, and so you can tend to reduce the bandwidth of notches driven by that method further. If you use bidirectional D-shot or ESC telemetry-based RPM data and you use the multi-source option to apply a notch on every motor, you're likely to be able to make the bandwidth even narrower because the targeting of the notch is going to be even more accurate. If you're using a less precise notch targeting method, you'll need to make the notch bandwidth larger in order to prevent noise bleeding through either side of the notch. In any case, you're just going to go as far as you can until you start seeing noise bleeding through, and then back off a little bit so that you find the ideal value. That's going to give you the minimum delay while still giving you good noise attenuation performance. Now that your harmonic notch filters are correctly tuned and optimized, they should have had a drastic effect on the noise profile that you see in your logs in the filter review tool. Before, you may have seen peaks like this that indicate motor noise, and you may have seen one at the fundamental frequency, and there may be a little second one and a third hump of motor noise. Once the notches are correctly applied with RPM data, they will just crush all of that noise out completely, and you may not be able to see any of it. This is what I get after setting up the filters on my UL8. There's no real visible motor noise anymore. Once we've done this, we can now circle back to the gyro low pass filter, and we should be able to gradually increase it, and perhaps in some cases increase it quite significantly, depending on how well our notch filters are taking care of the main sources of noise. You'll find INS gyro filter in the full parameter list in the config tab in Mission Planner. Increase it gradually. Take it one step at a time. Don't increase it a lot in one go. Just take it step by step. And you want to increase it as far as possible while keeping any peaks of post-filter noise below about -50 dB or even lower if possible. When you are raising the INS gyro filter cutoff frequency, listen for any oscillations. Make sure to check the motor temperature on the drone after a short hover.
If you hear any audible oscillations or the motors come down hot, that may indicate that you have insufficient filtering, but it may also indicate that there are problems with the PID tune, which we're obviously going to look at in future videos.